Have you ever like read one of those health headlines? The one screaming coffee cures cancer or this new vaccine prevents disease. And you just sit there and wonder, um, how did the scientists actually prove that?
Oh, yeah. I mean, we see those flashy headlines literally every single day.
Right. And well, I always think back to the 1980s. There was this entire generation of doctors who prescribed a heart medication that actually it ended up killing more patients than it saved.
It's terrifying to think about, and the reason thousands of brilliant, highly trained cardiologists got it so tragically wrong was because they relied on, observational logic.
Yeah,
They didn't rely on the brutal, unyielding math of a rigorously designed clinical trial.
exactly. And that is why today we are taking apart the actual machine of medical research. We are diving into the review materials from the basic course in biomedical research.
Right, which is originally approved by the Board of Governors in partnership with the ICMR National Institute of Epidemiology.
It's basically the foundational playbook, the curriculum that teaches medical professionals how to, stop guessing and start actually proving things.
Because we constantly see the finished products of this machine, right? The headlines, the new drug approvals, but we very rarely look at the scaffolding underneath.
And that is exactly our mission for this deep dive.
Yeah.
We are going to build you the ultimate scientific BS detector. We'll walk you through the entire life cycle of a study.
So that the next time you see a claim that, I don't know, a certain diet prevents Alzheimer's, you can look right past the headline.
You can evaluate the architectural bones of the research itself.
Okay, let's unpack this. Before anyone puts on a lab coat or, hands out a pill, where does the actual architecture of a study even begin?
Well, it begins with a surprisingly simple human state. Uncertainty.
Uncertainty.
Yeah, I mean, research doesn't start with an answer. It starts because a group of investigators identify a very specific gap in our knowledge about a population.
But the very first trap researchers fall into is failing to define that uncertainty. You really have to translate a vague curiosity into a highly engineered research question.
Because, you can't just walk into a clinic and say, hey, I wonder if diabetics should exercise daily.
No, not at all.
It sounds like a normal question to ask, but scientifically, it's pretty much useless,
It
right?
is completely useless. I mean, think about all the hidden variables in that one sentence. What kind of diabetes? Type 1 or type 2?
Right, right.
And what kind of exercise? Are we talking about, like, a leisurely 10-minute stroll, or are we talking heavy resistance training?
Yeah, big difference.
And what exactly defines should? Are we measuring weight loss or mood or blood sugar?
So to make it scientific, it needs strict boundaries.
Exactly. A refined version of that would be something like, does brisk walking for 1 hour daily reduce fasting blood sugar in type 2 diabetics?
Okay, that makes sense. That gives you a literal blueprint. You have your population, which is type 2 diabetics, your specific exposure, which is brisk walking for 1 hour daily, and then a tightly defined, measurable outcome reducing fasting blood sugar.
Right. You know exactly what data to collect.
But even a beautifully constructed question like that still has to pass a crucial filter, doesn't it? Before anyone commits, years of funding to it.
Oh, absolutely. It has to pass the FINER test. That's FINER.
Right, which stands for feasible, interesting, novel, ethical, and relevant.
Exactly. So feasible means you actually have the statistical power, the technical expertise, and, well, the budget to actually pull it off.
Because science is expensive.
Very. Then interesting and novel mean you aren't just reinventing the wheel, you are confirming, refuting, or extending what we already know.
Got it.
Ethical, obviously, means an oversight board won't shut you down for harming people. And relevant asks the ultimate so what test. Does this actually advance human health or influence policy? If a question isn't finer, it just dies right there.
Okay, but let's say it survives. You have a finer question. Now you have to decide what kind of study to actually build. And the source materials divide the entire world of research into two massive buckets based on your objective, right? Descriptive and analytical.
And the distinction between those two dictates literally everything that follows. So descriptive studies are purely observational.
Okay.
You are just trying to measure a quantity. The operative verb you use in a descriptive protocol is almost always estimate.
Estimate.
Right, like you want to estimate the prevalence of physical activity in a specific city. You are answering the who, what, when, and where.
So if I just want to know how many people have a disease, That's descriptive.
Mhm.
But the second I want to know why they have it or what's causing it, do I really have to step up to an analytical study? Is it really that black and white?
It really is. Analytical questions are all about testing a hypothesis. They involve comparisons. Here, the verb you use is usually determine.
Right.
You want to determine whether, say, a high-sodium diet increases the risk of hypertension compared to a low-sodium diet.
So a descriptive study has no comparison group, but an analytical study must have a comparison group.
Exactly.
Let's ground this with some actual scenarios to see how it plays out.
Okay.
I want to frame this as a bit of a pop quiz for you, drawing directly from the exact MCQs in the source text.
So, all right, let's do it.
Scenario 1. A doctor at a tertiary care hospital in Sikkim suddenly identifies 18 cases of Creutzfeldt-Jakob disease, which, is incredibly rare.
Very rare. Yeah.
They write a paper detailing the clinical and laboratory features of these 18 patients. What exactly is the scientific value of that?
So what you're describing is a case series. It's a descriptive study, and its value is strictly as a flare gun.
A flare gun.
Yeah, the doctor has found a highly unusual situation and is documenting it just to alert the medical community. But structurally, because there is no control, group-like, no comparison to healthy patients, that paper cannot test a hypothesis.
It can't tell you why those 18 people got the disease.
Exactly. It can only generate a hypothesis for someone else to go test.
Right. So to find the why, we need to build an analytical study. Let's try another quiz scenario from the text. Say you're a pediatrician. You've got 120 children suffering from Crohn's disease.
Okay.
You suspect their early diet might have played a role, specifically whether they were exclusively breastfed.
Yeah.
So you recruit those 120 sick kids, and you match them with sibling controls. And then you look backward at their history of breastfeeding. What kind of study is that?
That is a classic case control study.
Case control.
Yes, because look at the order of operations. You start with the disease, the cases, those 120 kids who already have Crohn's, and then you look backward in time for the exposure.
You act like a detective looking backward for the suspect.
Right. But how you measure that link mathematically is tricky. In a retrospective case control, you artificially decided to bring in exactly 120 sick kids and 120 healthy siblings.
Right.
Because you rigged that denominator, you cannot calculate a true real-world risk or incidence rate. You can only calculate the odds.
Ah, which is why the measure of association for a case control is the odds ratio.
Exactly. You are calculating the odds that the sick kids were exposed compared to the odds that the healthy kids were exposed.
Okay, next scenario. What if investigators recruit 1,000 diabetics and 2,500 non-diabetics?
Right.
They make sure none of them have cataracts at the start,
Right.
and they follow them for 10 years to see who develops cataracts.
Now that is a prospective cohort study because they didn't start with the disease. They classified the groups purely based on their exposure status diabetes versus no diabetes.
And then they move forward in time.
Exactly, prospectively waiting for the outcome to happen. And because they are tracking a natural population over time without rigging the numbers, they can calculate the actual incidence rate.
So the measure of association here is relative risk, not the odds ratio.
Exactly. You get a much higher quality of evidence.
Okay, last pop quiz question. A researcher uses old medical records to classify past patients based on whether they worked in coal mines, so exposed or unexposed, and then compares their lung carcinoma frequency. Wait, if it all happened in the past, isn't that just a case control with extra steps?
No, and this is a huge curveball. That is a retrospective cohort study.
Why?
It comes down to the chronological logic. Even though it looks in the past, the researcher grouped them by exposure, first working in the coal mine, and then traced the records forward in time to see the outcome, the lung cancer.
Oh, I see. The structural logic matters more than the actual calendar year.
What's fascinating here is how the direction of time and how you divide your groups completely changes the statistical power and validity of your findings.
That is fascinating. But, everything we've talked about so far is observational, right? The investigator doesn't manipulate the exposure. They just watch.
Right. And nature is messy. People who choose to eat healthy might also sleep more or have less stress. Those are confounders.
And observational studies can never fully escape them. But when investigators do manipulate the exposure, we enter experimental design, clinical trials.
Yes. The randomized controlled trial, or RCT, it is the absolute gold standard.
Let's break down why. It rests on two pillars, right? First is randomization.
Right. Randomization ensures participants have an equal chance of getting the standard treatment or the new treatment. This is literally the only effective method known to science to minimize both known and unknown confounders.
Because if doctors chose who got the drug, they might subconsciously give it to their healthiest patients.
Exactly. It completely minimizes selection bias.
And the second pillar is blinding. I understand blinding the patient because of the placebo effect. But why go to the trouble of triple blinding a study where even the data analysts don't know who got what?
Because human bias ruins data at every stage. Blinding eliminates co-intervention, which is when a patient knows they're on a placebo and starts taking extra supplements to help themselves.
Oh, wow. Yeah, that would ruin the data.
And it also eliminates biased outcome ascertainment. If an investigator knows a patient is on a highly anticipated new drug, they might interpret a symptom differently than they would for someone on a placebo.
They might write down mild fatigue instead of adverse event. And these RCTs happen in phases, right? The source breaks down the 4 phases of clinical trials.
Yes, it's like a gauntlet. Phase I is just up to 50 healthy volunteers. It's not even about if the drug works, it's purely about safety and finding a toxic dose.
Then phase 2.
Phase 2 expands to maybe 100 to 500 low-risk patients. You look at the dose and early efficacy.
Does it actually do anything?
Right. Then phase 3 is the massive one, 1,000+ high-risk patients. This is about effectiveness. Does it work better than what we already have?
And if it passes, it hits the market. But the research doesn't stop. Phase 4.
Right. Phase 4 is post-marketing surveillance. This is community-based, thousands of people just hunting for those 1 in a million rare side effects.
Okay, so getting the data is only half the battle. According to the notes, researchers have to be really careful when they actually analyze all this data. They have to avoid data drenching and post hoc analysis.
Oh, this is a huge trap. Data drenching is when you just dump all your data into a computer and run every statistical correlation imaginable until you find something that looks positive.
Just fishing for results so you can get published.
Right. But it's meaningless noise. You have to lock in your analysis plan based on your original finer question.
Which brings us to the types of errors you can make. The notes talk about random error versus systematic error.
Yes, random error is just due to chance. Think of a shaky archer. The arrows hit all around the target, but if you shoot 10,000 arrows, the average will hit the bullseye.
So you just increase the sample size to fix random error.
Exactly. But systematic error, or bias, is a flaw in the system. It distorts results in one specific direction, like a bathroom scale that's permanently stuck 5 pounds too heavy.
Stepping on it 1,000 times won't fix the number.
No. The only way to fix systematic error is to improve the actual study design.
Now, there is one specific error I want to talk about, type 2 error. The MCQ definition from the text says it occurs when the null hypothesis is not rejected when it is false. That's a mouthful.
Yeah, it is. Think of it like a courtroom. The null hypothesis is the assumption of innocence. It means your new drug does nothing. A type 2 error happens when the drug actually does work. The defendant is guilty, but your trial fails to prove it. You miss a real effect that is actually there.
Why does that happen?
Usually because your sample size was just too small. The study didn't have enough statistical power to detect the truth.
And this is why this matters to you, the listener. When you hear a news report say, a massive new study found no link between this diet and cancer, your BS detector should go off.
Absolutely.
You should ask yourself, did this study actually have enough power? Or did they just commit a type 2 error? Absence of evidence is not evidence of absence.
Exactly right.
So what does this all mean? We started with a finer question. We chose a descriptive or analytical design, we observed cohorts, we built gold standard RCTs, and we crunched the numbers while dodging bias. It means research is a rigorous, highly structured machine designed to turn human curiosity into undeniable facts.
It really is.
And you, the listener, now have the tools to look past the flashy health headlines and see the architectural bones beneath them.
But, it does leave you with something to ponder. As our world becomes increasingly digitized, we have smartwatches tracking our heart rates constantly, AI analyzing medical records in real time.
Yeah.
Will this traditional, incredibly slow life cycle of clinical trials eventually be replaced? Will we shift to massive, instantaneous, ongoing observational studies?
Oh, wow.
It makes you wonder, are we all already participating in the largest cohort study in human history without even realizing it?
That is wild to think about. Just existing in the digital age makes us part of the data set. Something to chew on next time you check your steps on your watch. Thanks for joining us, and we will catch you on the next Deep Dive.